Do you see my screen?
Yes, great. Our second speaker is Bahador Bahmani. He will be giving a talk on a resolution-independent neural operator. Bahador Bahmani is a postdoctoral fellow at Johns Hopkins University. He obtained his PhD in engineering mechanics from Columbia University in 2024. Bahador's research lies at the intersection of computational mechanics and scientific machine learning, focusing on developing a scalable algorithm for forward and inverse problems in data-driven solid mechanics. He also has industrial research experience in computational geometry and machine learning within the additive manufacturing and data security sectors. With that short introduction, the floor is yours and you can start your presentation.
Thanks for the introduction and thanks for the invitation. Okay, let's start. So can you hear me?
Yes.
Great. I'm gonna present our recent work on resolution-independent neural operator, which is basically, I'm gonna provide the results mostly from our recent paper, which is available on arXiv, and it's a joint work with Somdara Goswami, Yanis Kabrikeris, and Michael Shields. I will give some background about operator learning and set up the notation and what type of problem I'm interested to solve, and then we go to more details about our approach. So operator learning, basically, in this context, we have some functions UX, which is defined in well-defined input functional space. And there are some operator that acts on the functions and maps it to another function, which is like, for example, here, S of Y, which is also defined in a well-defined output functional space. And importantly, the domain of these two functional spaces, which for one is X and the other one is Y, are not necessarily similar. And an example of this type of problem, we can look at like this Berger's equation here, and maybe one is interested to map from initial condition, which is UX, and define on the 1D domain to directly get the space-time solution, which is the space-time, which is the two-dimensional in the space-time as output functional space. And in that setup, we basically assume we have some realization of these US pairs, which are sampled from some probability measure U. And under empirical risk minimization, we are trying to recover or approximate the operator G by parameterized functional, which is capital F with some parameters theta. There could be multiple ways to formulate this type of problem, but here we are mostly focused and interested in DeepONet, which its vanilla architecture is introduced in 2019, which is an extension of Chen and Chen work for deep. The theoretical part is the extension of the Chen and Chen work from shallow network to deep networks, which is, the idea is interesting, and the way they formulate this operator learning task is quite flexible. It has been shown a lot of promising results so far, and flexible in the sense that you can work, plug and play any type of neural network architectures. And beautifully, it has theoretical guarantees. There could be other approaches such as Fourier neural operator, but that's not the target of this talk. So in that sense, in the DeepONet, we basically have two sort of sub networks. One is BranchNet and the other one TrunkNet. So BranchNet try to capture the information from input function, which basically you have to pass a discretized version of your input function to the BranchNet to produce some coefficients for you. And in the parallel, TrunkNet tries to operate on the output functional space and produce some bases compatible with the output functional space. And a dot product between these two gives you sort of a hypothesis class to approximate your operator. Okay, what's the motivation of our study is we are interested in resolution dependency. And in that sense, vanilla or DeepONet could have two sources of resolution dependency. From the output function space, where trunk net is applied, because it directly by using multi-layer perceptron, you can directly operate on the output function domain, and in that sense, there is no issue in terms of resolution dependency from the output function perspective. And that's why from the output function perspective, you can easily work on point cloud samples of your function realization. The issue comes to the input function perspective, where basically because of in any case neural networks are operate in vector spaces, you need to have sort of a vector representation of your input functions, and in that sense, the vanilla approach works on a discrete, like you have to pass the discretized version of your input realization, and that's why you have to operate with the discrete version of your input function domain, not exactly the continuous version of it. And that's where the resolution dependency comes to the picture. And for that reason, for people who work with vanilla DeepONet, they may find that like all the discrete, all the points that you basically, we call it input sensors, has to be aligned to each other from realization to the other. Okay, so should we care about this sort of problems? It turns out yes, because in complete, like we could have like the sensor could be malfunctions from one experiment to another, or you could, in the computational sense, many times we have to operate on meshes with completely different number of mesh, or different density in terms of the how refined are. And in the multi-fidelity, multi-skill scenario, we also need to think of, we have the data from different skills that are not necessarily aligned. Okay, the way we think to tackle this issue is that the question is that if we can find the consistent vector representation, which basically for each realization of your function as a point cloud, which are not necessarily aligned to each other from one realization to the other, is that possible to find the vector representation for each of them that has the same number of dimension, and each dimension are consistent with each other from one realization to the other? In that sense, if this is possible, then we can pose the same operator learning statement, but now working with this vector representation, which hopefully is compact and with less dimension than the initial discretized version. But this representation should be resolution independent. So we use the ideas like basically what we want to do is that we want to represent the functions with some vector, and there are many ideas to do that. But here we got like inspiration from like the classical ideas how to use functions against functions, in the sense that if you have some set of orthogonal functions, you can uniquely represent a function of your interest, and for that, like you can go from function u to some coefficient that are vectors back and forth. And now the question is that how we can find these basis functions in a data-driven manner. So one can say,
can I ask you a question?
Sure.
You could add here a neural network, because actually when we first proposed this DeepONet, what I was thinking is that you could have a, since you have measurements of the function, you can represent with a neural network, another neural network. So the
that's this work.
The basis would be not the coefficients of the KL expansion, but actually the last hidden layer. That will be the basis. Is that what you're doing?
This is exactly. I'm gonna go to the introducing, like replacing the bases with neural networks.
Okay. All right. Go ahead.
Okay. Sure. But one key here is that we are interested to have those bases to be orthogonal to each other, because that gives us a unique representation. Otherwise, you cannot go back and forth between functions to vector space and so on. Okay, so the predefined bases could be suboptimal. So these type of question can be answered in a field in machine learning called dictionary learning, and probably we have already worked with dictionary learning, but maybe we were not aware of that. So first, the classical dictionary learning concern is concerning basis vectors, not basis functions. And like the examples of this method here are PCA or POD, which is proper orthogonal decomposition. But most of those things operate with basis of vectors, and the reason is that because in a way they are dealing with singular value decomposition that require aligned measurements. And again, this introduced dependency on discretization. And an example here you see, this is the measurement matrix from like n realization, and basically the columns should be corresponding to each other from one realization to the other. Otherwise, the SVD doesn't make sense in that sense. And what we are interested to do is to have a function space dictionary learning. Instead of learning basis vector, we want to learn basis functions. And the idea is simple. Basically, if we are at the first place, we are interested to directly operate the function domain. So for that reason, for that, you can use a multi-layer perceptron. And if you have a bunch of these, now you have a set of basis functions that builds your dictionary. And let's set up some data structure and what we are expecting as a data in our approach. So for ice realization, which is a signal on some point clouds, and you can see here we have some points in a bag, which is our point cloud, and we don't assume any order and any relational information between these points. And each point in this bag is a tuple of like a measurement location and the signal value at that location. And so this is our data structure we assume, and that's why you see from one realization to the other, we don't assume the number of points are the same, or their location could be different. And we have for the approximation, we assume like reconstruction hypothesis by reconstructing in a linear combination of what we have in our dictionary. Under this setup and this dictionary, you see here the theta are unknown. Those are the parameters of neural network, and their coefficient is also unknown. Under that setup, we are interested in this type of optimization problem that we want to minimize the signal of our interest by these basis functions that are shared across all realization, and some coefficients that are trying to adjust per realization. And we have some like inductive bias, like a sparsity regularizer, which can be played around by different ideas. So this is the type of problem we are interested to solve. Sure.
Yeah, I have one question. Here, do we require the basis by the neural network to be orthonormal?
Orthogonal is necessary, but unit normal, no.
Okay, but how do we do it in here?
Where?
So, for example, here is the precise neural network.
So I'm gonna discuss that.
Okay.
It's to a slide. Okay. So we have multiple like.
No, I think you can do it like in the two-step DeepONet where you can get the basis and then you do a QR or a SVD on the basis. You can also normalize it.
Yes. Yeah.
I don't see it could be related, but not directly like that.
Yeah, but I don't see. I mean, that's not a showstopper.
Okay. Okay, so we have a dictionary which at the beginning you don't have anything. It starts from 0, but let's assume here you have some not trained bases, and your objective is this kind of objective here. But there are multiple challenges. So the first challenge is that your basis and coefficient at the same time they are unknown. So this is a very ill-behaved optimization problem. And the second challenge, because of the unique representation, we need orthogonal neural network bases. And the third challenge, sometimes not required, but sometimes it's desirable to have unit norm bases, because that helps optimization, and also it has the interpretability component, because after that, the coefficients tells you how much each basis contribute to your reconstruction. Okay. So the first part, in terms of optimization, we use ideas from ADMM. Basically, you assume you have some sort of correct basis parameters. You don't focus on that. You just try to do the best optimization to best estimation of the coefficients. And once you have that, the second step would be just fix those coefficients, but increment in dictionary in a way that the reconstruction error just reduce. Okay. That's the way we address the first challenge. So the second challenge is basically, if I give you some dictionary and you do your best to approximate that, the residual, which is a signal, is gonna be orthogonal to your basis subspace. And this is the fundamental concept that is being used in Gram-Schmidt process. For that reason, so what the algorithm in a nutshell is doing for building adaptively orthogonal bases that are parameterized by neural network, you first, by having your dictionary, you try your best to reconstruct. You have a residual, which is a signal on point cloud, and you initiate a neural network from scratch. That's the SciNu, and you try to train your neural network to capture the residual signal. And if this training is successful, basically your neural network is sort of weakly orthogonal to your basis subspace so far. Okay. And in terms of unit norm, so we have two ideas to make the basis unit norm. The first one, which is easier, and I call it offline, is that you at the first place, because you do this stuff adaptively. Each time you just focus on one basis. You don't care about the being unit norm. You just trained whatever it has, and after training, you just normalize. Basically, you can estimate the norm of your neural network by generating some points in the domain and estimate the norm of the basis. And when you want to add the dictionary, you just rescale. The other way, which is online, actually uses ideas similar to layer normalization, which is common in machine learning. But here, the unconventional part is we do it in the output layer. Basically, during the iteration, you again use your points to estimate the norm of the norm of your basis and rescale every time, every iteration. Okay, so far whatever I told you is just general basis. As long as it's a MLP type, it's gonna work. But here I'm gonna be more specific about the structure of each basis function that we inject during the training. So we use ideas from implicit neural representation, which has been shown successful in computer vision for signal representation. But in here, we use it as a basis function. And they are just a variant of MLP that suppress the spectral biases toward frequency content. And more specifically, we are focusing on siren architecture, which basically is just MLP with sinusoidal activation function, with a slight different way to initialize the weight and bias. Okay, so what is implicit neural representation? Basically, instead of storing signal as a discrete object, you can map from the location of the signal to the signal, which you can see it here from some location to the signal values. And in here, I'm just showcasing it's like a regular grid, but it doesn't matter. It could be whatever grid. And in that sense, the siren just maps from the grid to the field. And this could be, for example, one basis function. And once it's trained, the super resolution comes for free because you can just sample, you can just generate data finer. Okay, by far, people who are familiar with GAPI-POD may seem like there is some sort of relationship between.
It was developed at Brown. It was developed in our department by Sirovich.
Oh, interesting. Great.
In the mid-80s.
I didn't know that. Thank you for letting me know that.
Okay.
It's a seminal work. It's beautiful.
Larry Sirovich.
Yeah. Okay. So there is a subtle relationship between the way we are doing dictionary learning and GAPI POD. So simply GAPI POD extend POD for signals that have missed values. But it still treat data in a fully discrete manner. And at the end of the day, it gives you basis vectors, not basis functions. And they are just defined on the union of the measured location for you. So in that sense, you don't have access to the smooth differentiable basis functions that continuously define everywhere in your data set. Okay, here we have this simple example to showcase some aspects of our work in the sense of dictionary learning. Basically here, we have manufactured three basis functions, psi1, psi2, psi3, which are visually depicted in here. And like the psi1 is a sixth order Legendre polynomial, the psi2 is the cosine, and the psi3 is the ABS, like absolute value function. And intentionally, psi2 and psi3 are not orthogonal, but we are using these by linear combination of them to generate some signal. And how we do that? We basically sample randomly from a standard Gaussian to generate some coefficients and just linearly add those things. And in here, you see the signals, which each column is the realization, and each row is the value of the signal at the particular location in, like, let's say X space. And here we have like 200 realization, and that's why that matrix is 100 by 200, 100 by 200. Because we wanted to compare with GAPI POD, and we wanted to see like how we can recover bases from like dates from some measurements that are not aligned. So we have this kind of masking matrix after generating the data. We mask the information randomly, like the number of points, the location of the points are going to be different. And this is like, for example, 90% masking matrix. 90% information is not going to be used during the training to build the base, to find the bases and reconstruct the signal. So here you see the result for 50%. And the first row is corresponding result for GAPI POD, and the second is our algorithm. So you can see, like, without enforcing the orthogonality of the bases in a strict manner, and also the other property of the GAPI POD, which is like maximizing the variance per basis, we still find like a very correlated basis function for both approaches. And if we increase the amount of how much information is masked, at some point you see the GAPI POD will give you like bad results, but our approach is still operational. And this is not magic. This is because of that difference between basis vector and basis function. Here, the function is as the inductive bias, we put the smoothness over there because of that like MLP there. But in the GAPI POD, it doesn't have that kind of assumption. That's why it failed. But if we increase, our approach is going to be also failed, but in this setting. So in terms of orthogonality check, you see GAPI POD has to be by construction orthogonal, and that's why you see everything here is dark. In our algorithm, which was enforced weekly, is still we see we can get a relatively orthogonal base. Okay, so here this is an interesting.
Again, I have one question. So you have two ways to enforce the unit norm, the offline and online. Which one is better from experience?
So the offline one is easier. The online one is gonna, because particularly at the initial iteration, because it could shoot you to different places. So at the beginning, you have to be careful in terms of the learning rate, and then gradually increase the learning rate, and then just then decrease. So I would say the more robust in terms of optimization is the offline one. But we introduced two algorithms. For one of the algorithms, you have to do online. That's why we also have to do the online.
Okay, yeah. Thank you.
Sure. Okay, in here, this is the test results for for some data which was masked by 85%. And this is in test. There are like two different regimes of the behavior here that I call it in distribution extrapolation, which are the regions by purple, and in distribution interpolation, which I show by green. And I will explain why, what those things means. If you look at here, I said, can you hear me? Can you hear me?
Yes, Bahador.
Yes, yes.
Oh, sure. So if you look at here, the 50% data that we use for identifying the bases and reconstruction are shown by these little circle blacks. And the red dots are just the ground truths which are masked. And the blue line is the reconstructed field by our approach. Let's start with the green ones. So you see from this little point, the dark circle to this dark circle, we don't have any data point here. And that's why I call this interpolation, because both ends has some points, but in between there is no point. And our approach can reconstruct very well the reality of the behavior in both cases. And for the purple one, from one side, for example, in here, the left side, there is no data, but the right side, you have this little point here. And the other one, from the right side, you don't have any data, but from the left, you have this little point here. I call this in distribution extrapolation. Extrapolation in the sense from one side, you don't have any information. In distribution, because this is a sample from the function you are not out of distribution in the sense of the function realization. Again, here you can see you can reconstruct pretty well. And this is not magic. This is because we leverage the correlation structure among realization during the building of those bases. For example, if you wanted to do just the interpolation per realization, you couldn't, like, of course, you could get some line here, not like go up, or it could like go up, but for no reason it's go up. Usually it's gonna be just let's say you use SP line, it's gonna be just a straight line here. So this is important to construct the correlation structure in that sense. Okay, now we come to the RINO. So basically in RINO, what I told you covers the first aspect. Basically in an offline manner, you just focus in your input function realization and you try to build an appropriate dictionary based on what I told you. And once you have access to that dictionary, when it comes to the operator learning part, you basically, based on the dictionary side you already learned, you project any realization at inference or during the training to some vector space, representation alpha, and you pass alpha through the branch net, and the rest would be the same. So the rest of the structure is just a DeepONet. So that's where that's the kind of surgery we do at the first part. Okay, now we come to the numerical examples, and in here in the numerical.
I have a question.
Sure.
Do you have a theorem that shows that this is a RINO?
RINO.
How do RINO is defined by Mishra?
RINO by Mishra.
Some data knows. She was there in the talk.
Yes, yes. No, we haven't checked it. That was
a theorem to call something resolution dependent. You have to have a theorem.
Yes, we haven't done that, George.
So from the examples that you will sort of trying to say, okay, it's independent, right? Resolution.
Yes, yes. We haven't proved it theoretically through theory.
Yeah, we don't have the theory.
But that's not what the definition of RINO is. That's why I was kind of. RINO was the word RINO was introduced by Mishra in his paper.
George, he was actually saying resolution invariant, and this one we said it as resolution independent.
Okay.
But yeah, we haven't proved it theoretically till now.
Yes. Yeah. Okay. That's fine. That's fine. Keep going, Bahador. Sorry. Sure.
Yeah. Theoretical proof is not there, but empirically we show that, like, if you can find the representation that is learned by a point cloud and it's resolution independent, then Empirically, you have shown that, but not theoretically. Okay, in the verification example part, we basically at the first part we have some we only focus on the input function discretization to show the resolution dependency for that. And for that, because we wanted to compare with some like a typical problem in the literature, some of the data I'm going to show you are generated on a regular grid. So for that reason, during the training, we just mask the information and we just use the subpart of them, which are going to be different in terms of the number of like sensor points, and the location is going to be different from realization to realization in the training step, and also for the test. So here we have like 4 benchmark examples to show the resolution independency, antiderivative, nonlinear Darcy 1D, nonlinear Darcy 2D, and Berger's. And as I mentioned, you see the random here. This random corresponds to the random training. Basically, each, as I just mentioned, each realization is just some points, which are not the number is the same, and the location. And the random test is also corresponding to this setup. But to better study the resolution independency at inference, which you see these number of sensors, we just do the inference for the regular grid of with this number of sensors in 1D and in 2D, like it's going to be like 20 by 20 and so on. As you can see here, so for all the cases up to some level, we don't lose that much accuracy in terms of the order of magnitude, except for 2 of cases, which is nonlinear Darcy and Berger's, which for the corresponding to like these bottom numbers, which is very coarse. And this kind of makes sense because there is no magic there. We need to have a sufficiently rich sampled realization. Otherwise, we cannot reconstruct with, like, for example, with 1 point. And this is related to like a Nyquist-Shannon sampling. Basically, if you have some functions that like has a like frequency f that varies the information, you need to sample at least twice to recover the
Bahador,
function.
I didn't understand how you select the points. Can you please repeat? Because you're using a language which is a little different than mine. So can you set up the problem? So the number of sensors is random when you say random for overload. So are you choosing 100 points or 51 points? And every realization is different, right? But always
exactly here. So you see here.
Yeah. But you're
so
not, for example, can you mix 100 points in one realization and 20 in another realization?
Exactly.
But you're doing that or you're not doing that?
I'm doing this.
Okay, then can you explain this again, please?
Sure. So let's assume this this square. You generate some field over there by a regular grid. Okay. So to showcase this approach is capable of like a completely irregular, I randomly mask the information and I don't use it during the training.
So each realization is it has a random mask.
Exactly.
Okay. But
the
how
random
many
mask
realizations you have?
For this problem, 800. If I recall correctly from the paper. In the paper we mentioned that, but I guess it's 800 or
800,
like that.
800 realizations, and then in the table you actually show that you're coarsening.
Yes.
Okay, I got it. Yes, but you're never mixing. You always have 100 points per realization. Of course.
No.
No, you are.
They are. So in here they are masked, but I will show you some result which is not no mask. It's gonna be completely.
This one, just take me the antiderivative. We should all be able to understand the 1D example.
Sure.
Derivative. Can you just say it in plain English what it is?
Yeah, sure. Let's say in your data for antiderivative, if I recall correctly, you have 101 points, right?
Yes.
So let's say we have the first realization. You randomly mask like 30% of the information and just threw it away. The second one, let's say the ratio is going to be different. It's going to be 40%. Randomly select 40% and throw it away. And now you have this sort of data set to train.
So from the how many realizations you have total for the antiderivative?
I forgot. I just use it. I just download from the Lulu webpage.
You had 10,000, I think, right, Lulu? You had 10,000, right, Lulu?
Less than that, I guess it's less than that. I forgot.
Roughly 1,000.
1,000. Okay.
Yeah, around 1,000. Yeah.
So these numbers 151, 26, and 21. What does they mean?
So for this part,
yeah,
this is at inference. Okay.
Oh, this is just a pay point. Okay.
This is at inference.
Sure.
So the train was on random, but inference is on regular grid to compare.
Okay, I get it.
Everything clear? Or
yeah, clear. Thank you.
No problem. So I'm here to get more details about the data setup at like train and inference. You can see here the red dots are just gone, no information. So at the first stage, we have to reconstruct by those dictionary, and that's the reconstruction, and this is the reconstruction error. But here I'm showing you the worst case in the test data for the output prediction, which is S. So U is the input function, S is output function. And this is just corresponding to, as I mentioned, worst case, and which is like, this is the error distribution for test data in the sense of prediction for output function, which shows like a reasonably accurate result. And for Berger's equation, which we basically map from the initial condition to the space-time solution, the input is just this setup is similar to Paris Perdicaris setup in his physics informed paper, DeepONet, physics informed operator learning paper. So basically, we have this kind of mapping from the initial condition to a space-time solution. And again, in the initial condition, you see, for example, this is worst case scenario. The mask is 30%, but 25th quantile is like a 40%. As I mentioned, the number and the location are going to be different from one realization to the other. And this is the error distribution for the output function prediction. So in the worst case, we have like a slightly high error, and I guess this is because it's out of distribution. That makes sense. But mostly, on average, we are doing at least like two order magnitudes better than that. And these are all relative errors. Okay, not absolute errors. And this is the problem that just there is no business in terms of masking, because intentionally the data is generated on different meshes. So we solved the nonlinear 2D Darcy problem, but now from each realization has its own different mesh in terms of where it refines or the numbers and so on. And here I just show you the worst case in the test data, which corresponds to this in this distribution. And again, it's fairly reasonable results, I would say. And on average, we are doing like one order magnitude better than the worst case. Okay, so the other idea is that what we did for the input function, we can do it exactly for the output function to learn a dictionary for output function. And these training are completely separate. And you can see this as like a POD DeepONet, which for POD DeepONet, we learn like the POD mode corresponding to output function. But when you use POD, we are actually mesh dependent. Here we can leverage what we built here for output function to find such bases that make it resolution independent. And once you have access to these two bases, basically your training is just gonna be instead of like the operator which is mapping from U to S, now your training is just a branch net which maps you from this vector representation to the another. Basically, it maps from a set of coefficients from the input to a set of coefficients to the output. And this is the same result for the same problem, but the same story, which shows like again reasonable accuracy. Okay, so basically, in conclusion, we introduced a dictionary learning that can adaptively learn weakly orthogonal basis functions from point cloud signals. And based on that, a resolution-independent neural operator is established. And the embedding space here could be interpretable because the coefficient tells you how much contribution of each basis is for the approximation and reconstruction. And as a future work, now we have RINO is opening like the way for learning operator for multi-fidelity, multi-scale data, and on some data that are like arbitrary mix from experiment and computation, which the location could be not aligned. Okay, and thank you for your attention. You can find more information in our paper, and we acknowledge our funding source.
Thank you so much for your great talk. Now we open the floor for questions, like more questions. Do we have any questions from the audience for the speaker?
I have one more question.
Sure.
So Bahador, imagine you are you take this data. Oh yes, you replace everything you did with GP, because you can have random points, right, in GP.
Mm-hmm.
Plus, you can have actually the uncertainty of your interpolation.
Actually, that's a good idea. Yeah.
So did you compare with that, or another question? Did you compare with Roberto Molinari from ETH has a way where he's sort of he sort of does a random projection. That's how I would characterize it in your language, because he takes the inputs and reshuffles them, and he has written a paper on it. It's also in his thesis. Have you compared with him?
Actually, that work came to. Let me ask you. Let me answer the first GP one. So definitely it could be possible. It's possible to do it with GP, but I guess it's difficult to enforce orthogonality in GP. At least at this moment, I don't know. Neural network is more flexible in that sense because of the grade.
Why do you need the orthogonality?
Because you want something unique representation. Otherwise, the representation is not like corresponding to your sample from realization. For the trunk, you don't need it in the vanilla DeepONet. You don't need the orthogonality in trunk, because you just do a linear combination to approximate, and you don't care to be one-to-one with your field. But in the input function sense, you want to have a good idea about what you have at your hand as an input to condition on. So in that sense, you have to have like a unique representation from the input function perspective.
I don't think so. I mean, the Weierstrass theorem that you have there, it's a unique representation. It's a polynomial that's not orthogonal.
Yeah. Like, but I just inspired by that. But like,
but
let me explain it.
I actually, that was something that I didn't agree with the uniqueness that you said.
So let me give a simple example. Let's assume that I give you two. Let's forget about uniqueness. Now you have a two realization from the input, and these two give you the same representation. So in that sense, is that a well-posed problem to learn? Because you pass the vector, you pass this guy now, the representation to the operator learning task. If this is like a from many to one, then you cannot learn this.
Well, fine. I mean,
It doesn't help. Sorry.
Go ahead, Lulu.
Yeah, I think it doesn't have to be orthogonal. To be a uniqueness, it only requires to be linear independent, right?
Yeah,
That's true.
Linear independence, yes. But that's why.
It depends to the orthogonality.
Let me say because you said made some statements which are not correct in the mathematical sense. For example, all finite elements are based on a polynomial basis. The only reason you go to, when we do high order, like spectral elements, we go to orthogonal polynomials is because of what Lulu said, which is a linear independence. And if you take a x to the 7 power and x to the 8, it's very hard to see the independence. So because of the linear dependence as you increase, otherwise you could use just the Weierstrass, not the spectral representation. So I don't think that is. In fact, I believe
But
that
another,
yeah,
yeah,
go ahead.
go ahead.
No, go ahead.
I think in a way you have, like, in my opinion, in a way you need to have some unique representation, either like a linear independent or like orthogonality of the basis. Because if you have the problem with many to one, then the learning statement is not well posed. Like, you have the same representation for two different things.
Well, allow me to disagree. For example, I could do the same thing with Chebyshev basis directly. So let's say which is orthogonal basis and then do a high order. So I can take random points and do a Galerkin projection with a mass matrix, and I have orthogonal polynomials, the Chebyshev, or get all the general polynomials. And I can do the same thing. So then I have these alphas, which are the coefficients of the spectral expansion. Can I do that?
But you said you use the orthogonal basis.
Yeah, I do it because I like spectral methods. That's what I was born in that environment, but not it's not necessary.
Maybe I need to think more, but like I guess like this, if it gives you unique representation, because it's a simple thing. If you have some method that doesn't give you unique representation, do you agree this learning is not possible? This type of learning here.
Oh, yes, but
so in that sense, like I wanted to control the uniqueness, and that's why, like, I thought maybe like orthogonality is one way to control the uniqueness.
Okay, I'm not a reviewer of your paper, but I think someone will complain about the statements.
I will think more then. Thank you for bringing this up. And for the second question, which was the ETH work, actually this came to us, like to me yesterday from some data, and I tried to study hard to understand what they are doing, and it is different than like what we are doing here. First of all, they are interested in mapping operator to functions, not function to functions. And second, in the branch net, which is the conditional part to condition on input, they have bunch of, because they just work on boundary measurements, to regularize the problem and make it more stable for training, they have to have like for the same output, which is the coefficient field they are going to estimate, they have to have like a multiple different boundary condition on the surface. And that's why for them, the input is just not one realization. The input is like a L realization that they condition on to infer the coefficient field inside the domain. And their focus is to make the independency in terms of the number of L. So in this work, L is one. Basically, you condition on one function and you output the field. But for them, they condition on multiple realization corresponding to boundary measurements to output something. So that shuffling thing is on L, not on per function realization discretization. So it is so far my understanding it's a different thing, but I need to, like, I studied that from yesterday, but definitely I need to study more. That's my idea so far.
Okay.
Thank you. Do we have any other questions? Vivek, go ahead.
Yep, I have a question. So actually a question like, have you tried on problems with high, my name is Vivek, I'm a PhD student working with Professor Karniadakis. So I want to know if you had tried using this method on problem with high spatial or high spatiotemporal gradients in the solution.
High tempo. So for some of the example, like the length scale was, it depends how do you define high, like gradients. But for some of them, the correlation length for GP that we generate the realization is reasonably fine. For example, for the Berger's equation, I guess it was like I forgot, but it's you have like a variation, like a considerably good amount of variation. But so you can go to like a very abrupt, like a Dirac delta or jump. I haven't tried that.
Okay. Also, one more question I had was, in one of the test cases, I don't remember, you are using an implicit neural representation to learn the mapping of the input function. You're learning the mapping from the implicit neural representation of the input function to that of the output function, right?
For all the examples, the bases are INR. For each
INR.
basis is
Okay. Because I came across, like around last year, this time I presented a paper named Corel. I'm not aware, I'm not sure if you know about it. So
Corel?
there they were, Corel, yes. So they were using INRs to learn, like first an encoder INR and a decoder INR to learn the implicit representation of the input-output function separately. And then they learned the mapping between the INR representations of the input function to that of the output function. I think you are doing something very similar, right?
I haven't seen that work.
Let me just put it on chat in that case.
Yeah, that
I can quickly put it in chat.
I'm not aware of that work.
Yep.
Thank you for bringing that up.
No problem. Give me just 1 second, please. Yep, I put it there. Yeah. They were trying to do, yeah. Thank you. Great talk. Thank you. Thank you.
Thank you. Thank you for sharing this. No, I'm not.
I
haven't. Yeah, sure.
Yeah. Do we have any other questions from the audience? Yeah, I think there is no more questions. So you can continue your discussion with Vivek later through email. Yeah, thank you so much for your great talk. I want to thank our speakers, Jambu and Bahador, for their time today. And thank you everybody for joining us today. So now it's time to close the session. Have a great weekend ahead.
Thank you. Have a good day. Bye.
Bye.